In 1829, Nikolai Ivanovich Lobachevsky, a Russian mathematician, published a work that would forever alter the course of geometry and, by extension, our understanding of the very fabric of space. This paper, on the principles of geometry, presented a radical departure from Euclidean geometry, a system that had reigned supreme for over 2 millennia. Lobachevsky's work dared to question one of Euclid's fundamental postulates, the parallel postulate, and in doing so they laid the foundation for what we now call hyperbolic geometry, a cornerstone of modern mathematics. And to appreciate the significance of Lobachevsky's contribution, one must understand the historical context in which it arose. Euclidean geometry, as presented in Euclid's Elements around 300 before Common Era, was built upon a set of 5 postulates. The first 4 were seemingly self-evident assumptions concerning points, lines, circles, and right angles. The 5th postulate, however, was a different animal altogether. It stated that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than the 2 right angles. This statement, while intuitively plausible, lacked the self-evident nature of the other postulates, and for centuries, mathematicians attempted to prove it as a theorem derived from the other. Efforts to derive the parallel postulate from the others proved fruitless. Mathematicians such as Ptolemy, Proclus, Ibn al-Haytham, Omar Khayyam, and John Wallis dedicated considerable effort to this endeavour, attempting to prove it as a consequence of the other axioms. These attempts, while ultimately unsuccessful, indirectly contributed to the development of non-Euclidean geometry by exploring the consequences of alternatives to the parallel postulate. Girolamo Sacchari, an Italian Jesuit priest, made a particularly notable attempt in the 18th century. He considered a quadrilateral with 2 equal sides perpendicular to a base and attempted to prove that the remaining 2 angles must be right angles, thus validating the parallel postulate. Sacchari considered 2 cases where these angles are either obtuse or acute. While he successfully eliminated the obtuse angle case, he failed to definitively dismiss the acute angle case, instead arriving at results he deemed repugnant to the nature of the straight line. Ironically, Sacchari was closer than he realized discovering non-Euclidean geometry. During this period, Carl Friedrich Gauss, arguably the preeminent mathematician of the era, also investigated alternatives to the parallel postulate. Gauss independently developed many of the ideas of non-Euclidean geometry, yet he hesitated to publish his findings, fearing the controversy and ridicule that might ensue. This reluctance highlights the prevailing intellectual climate, which considered Euclidean geometry to be the only conceivable description of physical space. Gauss privately corresponded with several mathematicians, including Farkas Bolyai, sharing some of his insights but urging caution regarding publication. Farkas Bolyai's son, János Bolyai, also independently explored non-Euclidean geometry. János, unaware of Gauss' work, dedicated a significant portion of his life to this pursuit, eventually publishing his findings in 1832 as an appendix to his father's textbook. Entitled The Science Absolute of Space, Bolyai's work, like Lobachevsky's, demonstrated the possibility of a consistent geometry that rejects the parallel postulate. Lobachevsky's 1829 paper, written in Russian and initially published in the Kazan Messenger, a relatively obscure journal, marked a turning point. He presented a geometry in which the parallel postulate was replaced with the assumption that, through a point, outside a given line, there exist at least 2 lines parallel to the given line. This single alteration had profound implications. In Euclidean geometry, given a line and a point external to it, there exists exactly 1 line through the point that lies in the same plane as the given line and never intersects it, regardless of how far it is extended, which is the parallel postulate. Lobachevsky's work replaced this by presuming many such lines exist. This seemingly small change led to a cascade of unexpected results, giving rise to a geometry dramatically different from the familiar Euclidean world. In Lobachevsky's geometry, the angles of a triangle sum to less than 180 degrees. The circumference of a circle grows exponentially with its radius. Parallel lines, in the Euclidean sense, do not exist. Instead, one has asymptotic lines that converge in one direction and diverge in the other. The geometry describes a space that is negatively curved, akin to the surface of a saddle. Lobachevsky meticulously developed the trigonometric formulas and geometric relationships within this new geometric framework, demonstrating its internal consistency and logical coherence. A key aspect of his work was the recognition that this alternative geometry was free from logical contradictions, which challenged the prevailing belief that Euclidean geometry was the only possible geometry. The immediate impact of Lobachevsky's work was minimal. Published in a relatively inaccessible journal and written in Russian, it attracted little attention from the wider mathematical community. Moreover, the very idea of a non-Euclidean geometry was so foreign and counterintuitive that many mathematicians dismissed it outright or struggled to grasp its implications. Gauss, upon reading Lobachevsky's work, recognized its significance and privately praised it, yet he refrained from publicly endorsing it due to his long-standing fear of controversy. The reception of Lobachevsky's ideas was initially met with skepticism and, at times, outright rejection. His contemporaries, deeply entrenched in the Euclidean framework, found it difficult to accept the possibility of a consistent alternative. The lack of immediate practical applications also contributed to the initial indifference. Geometry was primarily viewed as a tool for describing the physical world. Euclidean geometry seemed to suffice for this. Despite the initial lack of recognition, Lobachevsky persisted in his work, publishing further papers elaborating on his ideas and exploring their implications. He served as a professor and later rector at Kazan University, continuing his research and teaching despite facing considerable resistance and misunderstanding. In the decades following Lobachevsky's death in 1856, his work gradually gained recognition and acceptance. Mathematicians such as Eugenio Beltrami, Arthur Cayley, Felix Klein, and Henry Poincaré played crucial roles in popularizing and further developing non-Euclidean geometry. Beltrami, in particular, provided concrete models of hyperbolic space within Euclidean space, demonstrating its consistency and dispelling the notion that it was merely an abstract mathematical curiosity. One celebrated model is the Klein model. Using this model, it is possible to define straight lines in hyperbolic space as straight lines within a circle on the Euclidean plane. The Poincaré disk model is another example, where hyperbolic space is defined within a Euclidean disk, with hyperbolic straight lines appearing as arcs of circles orthogonal to the boundary of the disk. These models provided tangible visualizations of non-Euclidean geometry, greatly aiding in its comprehension and acceptance. Klein's Erlangen program, which classified geometries based on their underlying groups of transformations, provided a unifying framework for understanding Euclidean and non-Euclidean geometries as different instances of a more general concept. Poincaré's work on automorphic functions further solidified the connection between non-Euclidean geometry and other areas of mathematics, demonstrating its relevance and applicability beyond the realm of pure geometry. The development of general relativity by Albert Einstein in the early 20th century provided a profound physical application for non-Euclidean geometry. Einstein's theory describes gravity as a curvature of spacetime, with the curvature determined by the distribution of mass and energy. In this framework, the geometry of spacetime is generally non-Euclidean, and the presence of massive objects warps spacetime, causing it to deviate from the flat Euclidean geometry that we experience in everyday life. Lobachevsky's hyperbolic geometry, along with other non-Euclidean geometries, became essential tools for understanding and modeling the universe on a large scale. The legacy of Lobachevsky's work extends far beyond mathematics and physics. His daring departure from established norms and his willingness to challenge fundamental assumptions served as an inspiration for generations of scientists and thinkers. His work demonstrated the importance of questioning established dogma and exploring alternative possibilities, even when they seem counter-intuitive or absurd. Lobachevsky's geometry also had a profound impact on the philosophy of mathematics. It challenged the Kantian view that Euclidean geometry was a priori truth, a necessary condition of human thought. The existence of consistent alternative geometries demonstrated that geometry was, in fact, an empirical science, subject to verification and falsification through observation and experiment. Several specific mathematical and scientific developments can be traced, although sometimes indirectly, to Lobachevsky's work. For instance, the study of differential geometry, which plays a crucial role in general relativity and other areas of physics, owes a debt to the development of non-Euclidean geometry. The concept of curvature, which is central to differential geometry, was first explored in the context of non-Euclidean spaces. Similarly, the theory of Lie groups, which is used to describe continuous symmetries in physics and mathematics, has connections to non-Euclidean geometry through the study of isometries, transformations that preserve distances in these spaces. Furthermore, the ideas of non-Euclidean geometry have found applications in computer graphics, where they are used to model and render curved surfaces. A specific theorem developed by Lobachevsky, named after himself, connects hyperbolic geometry to Euclidean geometry. It defines a relationship between the angle of parallelism, a function of distance between a point and a line, in hyperbolic space and provides a basis for trigonometric functions within hyperbolic geometry. This theorem, while initially abstract, has found surprising connections to number theory and dynamical systems. Despite the initial resistance and lack of recognition, Nikolai Ivanovich Lobachevsky's On the Principles of Geometry stands as a landmark achievement in the history of mathematics. His bold questioning of the parallel postulate opened up new vistas of geometric thought, transforming our understanding of space and paving the way for some of the most profound scientific discoveries of the 20th century. It serves as a testament to the power of human curiosity and the enduring importance of challenging established paradigms, even when the path ahead appears uncertain and fraught with difficulty. Lobachevsky's legacy remains a reminder that the pursuit of knowledge often requires the courage to venture into uncharted territories where conventional wisdom yields to the boundless possibilities of the human imagination.